Hey everybody, Mr. Piercy here, and today we're going to be talking about a type of statement that geometry uses known as a biconditional statement. So what is a biconditional? Well, a bicycle is something that has two wheels. A biped is somebody like you and me, somebody that walks on two legs. So a biconditional, the prefix bi says that there's going to be two conditionals that we're going to be using. And we'll show you where they come from here in a little bit. But we're also going to be using the biconditionals to create definitions. And we'll explain about that here in a little while also. Now, the first thing that we're going to practice, this exercise that we have here with the creepy crawlies on our screen, is an example that geometry likes to use where we give you examples of what things are, and then we give you non-examples, and we use a little bit of deductive reasoning to see, okay, well, what do the examples have in common versus what the non-examples are missing? And we try to make a definition based off of the similarities of the examples versus the differences of the non-examples. Now here it's just kind of asking you to complete the conditional statement. How would you complete the sentence? If an animal is an insect, then where's the conclusion? What conclusion are we going to make? So what I want you to do is pause the video for a moment, figure out what your conditional or what your conclusion will be for the conditional statement, and when you're done, come back and check with me and I will show you what the conditional statement should finish like. Alright, so we're going to presume that you're doing what I'm asking you to do. Now looking at what the insects have, the insects all have 6 legs and 3 segments or 3 sections to their body, whereas the non-insects don't have 3 or 6 legs and they don't have 3 sections to their body. So that's how I'm comparing the examples of the insects, and I'm going to conclude that, let me get my cursor out of the way there. Go away, cursor. Then it has 6 legs and 3 body sections. So that is the conclusion to the conditional statement. Now moving on, we have a few things that we want to mention. Here's how the biconditionals are coming to be. A biconditional is going to be a statement that's created from the original conditional statement, and I'll underline that one in red, and I'm going to get crowded here, so let me pick another color. Let's do blue. So here, that is the converse, and you can see that's the converse because the hypothesis and conclusion of the conditional are reversed from each other. And so this symbol that we have right here with the P and the Q with the double arrow in between it, that is the biconditional. And what really makes a biconditional, or one of the things I should say, verbally, is the phrase if and only if. So one of the things that characterizes a conditional statement is the fact that it is written in an if-then format. But one of the things that characterizes a biconditional statement is it follows a format where we take the hypothesis and the conclusion, and in between we have the term if and only if. Now there's an additional thing I want you to make sure that you write down in your notes here. Let's see. Okay, biconditionals are true statements. So they have to be formed from true statements. Well, if the biconditional is formed from the converse and the conditional statement, then both of those originally have to be true. Now, if you recall, the conditional statement, the original conditional statement, its truth value is tied to the contrapositive. Meaning, if the conditional is true, then the contrapositive is true. Whereas the converse and the inverse, their truth tables, or truth values, I should say, those truth values are tied together. So this is one of the things that really makes a biconditional a powerful tool for us to use when we're trying to write a definition, is because essentially, if a conditional statement and its converse are both true, then every way that we could write a statement about it will be true, which is very helpful if we're trying to define what something is. So let's take a look at how we actually write a biconditional. We want to write a biconditional statement from the conditional statement that's given to you. And I know this is a typo right here that should say write the converse of the following conditional statement, not biconditional. So let's go ahead and real quick, not something that you need to do, but I feel the need to try and identify them. I'm going to identify the hypothesis, and then I'm going to identify the conclusion. Now that I've identified the hypothesis and conclusion, we can reverse the order to create a conditional statement that says, if two angles are supplementary, then the sum of the angles, or sum of the measures, is 180 degrees. So here I'm going to still go ahead and identify where the conditional, or where the conclusion and hypothesis are at. So that would be the conclusion, and this would be the hypothesis of the conditional. And you can see visually with the colors that their order is reversed. Now, since a biconditional statement must be written from two true statements, I want to know, is the conditional statement and its converse, are they both true or false? Well, let's look at the conditional. The sum of the measure of two angles is 180, and the two angles are supplementary. That is true. So the conditional statement is true. Looking at the converse, if two angles are supplementary, then the sum of the two measures is 180. That is also true. Since they are true, we can take the two statements and create a biconditional. Now, real quick, I want to come back up here to the table where we have the PQ combination. The way it's written like that is the way it's presented in pretty much every geometry textbook that you see. You know, we have our symbol here. We say the hypothesis, if and only if, then the conclusion. And that's how most people think about it. Now, if you're paying attention, you're going to notice that essentially the conditional and the converse are the same thing, just reversed. Since I can say the same thing both ways and it's still true, then that means I really can write the biconditional either way. I can write it as the hypothesis, if and only if, with the conclusion, or I could say Q with the double arrow like that, and P, and I could also say, well, the conclusion, if and only if, and then finish with the hypothesis. Now, most people don't think that way. We always think, well, the conclusion has to come second. So, but here we go. Here's our biconditional. Because a biconditional statement is reversible, we can write the statement one of two ways. The first way is, well, taking the original hypothesis of the conditional statement, followed with if and only if, and then the conclusion. And the other statement, same thing, just in reverse order. Either one is fine, simply because the hypothesis, or because the conditional statement and its converse are both true. So since reversing the statements didn't change its truth value, then we can write the biconditional either of those two ways. So what I want you guys to do in your notes is you have another one, another example. We want to take the conditional statement that's given to you and write a biconditional if we can. First thing we have to do is check to see what's the converse. Is the converse true or false? So we can compare it to the truth value of the original. If both of them are true, then we can write a biconditional. So at this time, I want you to go ahead and pause the video if you need to, figure out what the converse is, figure out the truth values of the two statements, and determine if you can write a biconditional or not. All right, so hopefully we're coming back after we've written down our answers. So let's go ahead and check. First of all, the converse statement is going to say if two angles are congruent, then the angles have equal measure. So I'm going to compare and say, okay, are these statements true or false? Well, the original statement that says if two angles are equal measure, then they're congruent, that's true. And the converse, if two angles are congruent, then the angles have equal measure, that is also true. Because they're both true, we are capable of writing a biconditional statement, and so here we are. Two angles have equal measure if and only if the angles are congruent. Now you could have written that the other way around if you wanted to, but I just wanted to write it like that this time, so that's how I did it. Now, what we're going to do is kind of turn it around, which is something that we do a lot in math. I'm going to take, now I'm going to provide you with a biconditional statement. I want you to identify what its conditional statement would have been. So we have a biconditional statement that says a ray is an angle bisector if and only if it divides an angle into two congruent angles. Now, most of us are still going to think of the beginning part of the statement as a hypothesis and the end part of the statement as a conclusion. So I'm still going to look at this kind of as the hypothesis, and we're probably still going to look at this. Oops, wrong color. Don't want the same color for the hypothesis and conclusion. So here's my conclusion. Now, identifying those two things, if you want to, you can kind of write it down on your paper here. What we want to do is now be able to write those in a conditional format, which we can say if a ray is an angle bisector, then it divides it into two congruent parts, and of course its converse, turn it around, and you're done. So that's how hard it is to write a conditional statement. It's really just kind of knowing, well, what's the conclusion, what's the hypothesis, and knowing the order that they go in. So try this next one and see how you do. Again, go ahead and pause the video, fill out your stuff on your notes, and when you're ready, come on back and see how you did. All right. So identifying the information here, again, this is not something that you need to do in your notes. I'm just doing it for visual purposes. Identifying the hypothesis, identifying the conclusion, so that way I kind of know where I want to put them into my statement for my conditional and converse. So here we wind up with a conditional if two numbers are reciprocals and the product is 1, or for the converse, if two numbers have a product of 1 and they're reciprocals. Now, keep in mind as we're going through this, if you have questions, because in class we did have a fair number of questions as far as, when something is true, when something is not true. If I have a true statement for a conditional but a false statement for a converse, what happens? So if there's something that you're not sure about, please make sure you write these things down as we go and address them to me when it's when you have an opportunity to shoot me an email or leave me a comment in our Google Classroom. So here, this is where we're kind of getting to the second part of what we were talking about at the beginning of the lesson. One of the things that we were talking about is we're going to be using biconditionals in order to be able to generate a definition. Now, the table that you have in your notes, this is the important bit right here. These are the three things that we're really going to be looking at to say, is something a good definition or not? A good definition uses clearly understood terms. Now, those understood terms can be something that intuitively people kind of understand what they are, or it could be a word that's already been defined at some other point. A good definition has to be precise, so we want to avoid words like these. These are not going to be something that we really want to help it, or that we want to use to define things, because what my interpretation of large might be and what your interpretation of large might be they might not be the same thing. So we want to avoid descriptors that can be interpreted differently. And this last one is really kind of the key, particularly since we're comparing it to the idea of a biconditional. Since a biconditional is reversible, a good definition should be reversible also. So let's see how we use this to make a definition. So here at the top of my screen it says, is the definition of the quadrilateral reversible? If so, write it as a biconditional. Now the definition that we have is a quadrilateral is a polygon with 4 sides. So, and when I look at the statement of quadrilateral as a polygon with 4 sides, that is true. Now I'm going to reverse it, which I've already done here on the screen. A polygon with 4 sides is a quadrilateral. Well, that is also true. Because both of these definitions are true, then that means we can write a biconditional. So you would have to be able to identify what is the hypothesis and conclusion, and I'm going to just write it like this. A polygon is a quadrilateral if and only if the polygon has 4 sides. So moving on, if you haven't already done so, we're going to kind of ask you to do the same thing on your own now. Same idea, write the reverse definition, see if both of them are true, and if they are, write a biconditional. So go ahead and pause the video now, and when you're ready, come back. All right, so here our reverse definition would say something along the lines of an angle that measures 180 degrees is a straight angle. Both the given definition and its reverse are true statements. So that means a biconditional can be written this way. An angle is a straight angle if and only if it measures 180 degrees. And the last thing we're going to look at is determining if something is a good definition or not. Now keep in mind, if you need to refer back to that table with those 3 particular things that clearly tell us what we're looking for to make something as a good definition or not. So again, I'm going to ask you to pause the video when you're ready and determine, are these 6 definitions, are they good or not? And if they're not a good definition, give a reason why. So when you're ready, pause the video, answer the 6 questions, and come back when you're done. All right. Now moving on, let's check to see how you did. A fish is an animal that swims. Well, that may be true, but it doesn't mean it's a good definition, because I'm an animal and I swim. At least I've been accused of being an animal from time to time. Anyway, here, animals that swim, there's lots of them that aren't fish, and so that means it's not precise, and it's certainly not reversible. So that's why it's a bad definition. Rectangles have 4 corners. Well, is it reversible? 4 corners have rectangles? Oh, that doesn't sound very good to me. And it really doesn't make any sense if you do it that way. And lots of things have 4 corners. Not just quadrilateral. I could have lots of things that have 4 quarters. They're not being very specific there. C, giraffes are animals with very long necks. Well, there's the very long. What does very long mean? It's not very precise. Ostriches also have long necks, so simply by saying a giraffe is something that has a long neck, am I going to look at an ostrich and say, oh, that's really a giraffe now? No, I'm not. It's not a very good definition. So an American penny is a penny, or I'm sorry, an American penny is a coin worth 1 cent. Let's see, can we reverse it? A coin worth 1 cent is an American penny. That sounds pretty good. That sounds good both ways. I think that's a good definition. We know what a penny is. We know what 1 cent is. So yeah, I'm going to say that's a good definition. Now, in class, a couple kids said, well, what about a rare penny? Well, that's the exception to the rule, maybe. So we'll just keep in general with what a penny is. You know, something you could reach into your pocket and find. Not something you have to go to a coin collector to get. E, a square is a figure with 4 right angles. Well, A figure with 4 right angles is a square. Yeah, that's true, but there's other things that are like that, because what about a rectangle? And let's see, a linear pair of angles are adjacent and supplementary. Let's see if we can reverse it. Let's see, a pair of adjacent angles are, let's see, can I reverse that? A linear pair of angles are adjacent and supplementary. Let's see, adjacent and supplementary angles form a linear pair. Yeah, that sounds pretty good reversed to me, so I'm going to take that one as a good definition. So again, keep in mind, can we reverse it? Does it avoid just vague descriptions, vague adjectives to tell you what it is? Does it use words that actually mean what they're talking about? So that's how we identify good definitions that we'll be using in geometry. Now at this point, the very last thing I want you to try and do, write your own examples of a good definition. Make some that are good, make some that are not good, and see what you can come up with. Share them with your classmates, share them in the comment section, see what you're able to come up with. But that's pretty much it for biconditionals, guys. Thanks for watching. If you have any questions, be sure to let me know, and I'll talk to you again soon. Until then, take care of each other. Bye.